1. Overview of the movement of continents and oceans. Today, most Earth scientists agree that continents and oceans are not fixed in place. Instead, they are constantly moving and changing their positions relative to one another. When we look at the edges of continents and oceans, we see that in some regions the Earth's crust is being compressed and pushed together, while in other places it is being stretched and pulled apart. Deep ocean trenches are often found close to the edges of continents, while in the middle of the oceans we discover long, high undersea mountain ranges. The shapes of the east coast of South America and the west coast of Africa are also strikingly similar, as if they once fitted together like pieces of a jigsaw puzzle. From all these observations, scientists realize that when continents move toward each other and collide, they can form high mountain ranges. When they move apart, the space between them can open up into new oceans. These repeated meetings and separations of continental and oceanic plates cause major geological events such as earthquakes, volcanic eruptions, the opening of new oceans, and the gradual disappearance of old ones. From this chain of evidence and reasoning, the theory of plate tectonics, also known as global tectonics, seafloor spreading theory, or simply the theory of moving continents and oceans, was developed. It quickly became the central framework of modern Earth science. 2. Earth's internal structure, the foundation of plate motion. To understand why tectonic plates can move, we first need to understand the internal structure of the Earth. We can imagine the Earth as a kind of layered sphere, similar to an apple, a solid central core surrounded by several different outer layers. At the very center is the core, which is denser and harder than the outer layers. It is thought to be made mainly of iron and nickel, along with some other heavy elements. The outer core is probably liquid because of its very high temperature, while the inner core remains solid due to extremely high pressure. Surrounding the core is the mantle, a thick, rocky layer composed largely of silicon and magnesium. For this reason, it is sometimes referred to as the SIMA layer. The upper part of the mantle is hot, but behaves like a soft plastic material that can slowly flow and deform. This layer is called the asthenosphere. It is roughly 150 kilometers thick, and it acts like a slippery base on which the rigid outer plates move. Above the mantle lies the crust, which includes both the continents and the ocean floor. The crust is rich in silicon and aluminum, and is sometimes called the SIL layer. Together, the crust and the uppermost solid part of the mantle form rigid plates that float and move on top of the softer asthenosphere below. In simple terms, the continents and ocean floors are not fixed. They are rigid plates sliding slowly over a softer, hotter layer inside the Earth. Recognizing this layered structure, especially the role of the asthenosphere, provides the physical basis that explains how tectonic plates can move. 3. From Wegener's continental drift to the theory of plate tectonics. At the beginning of the 20th century, very few people believed that Africa, South America, India, Australia, and Antarctica were once joined together as a single supercontinent. Ideas like that were considered extremely bold, even unrealistic. In 1912, the German scientist Alfred Wegener, 1880 to 1930, proposed the theory of continental drift. Although some scientists in the 19th century had hinted that continents might move, Wegener was the first to present a relatively complete hypothesis backed by many observations. To illustrate his idea, Wegener cut out the continents from a map and tried to fit them together. He found that the continents could be joined into a single supercontinent, which he named Pangaea. According to Wegener, Pangaea began to break apart around the time when dinosaurs first appeared, roughly 150 million years ago. In the early stage, Pangaea split into two large landmasses: O-Laurasia, including North America and Eurasia; O-Gondwana, including Antarctica, Australia, India, Africa, and South America. Later, Africa and South America separated from each other, and the Atlantic Ocean opened between them. At the time, Wegener's hypothesis was criticized as lacking a convincing mechanism, and was hard for many specialists to accept. His theory was treated somewhat like Galileo's idea that the Earth orbits the Sun, rather than the other way around. However, as more data on geology, geophysics, seafloor structures, and Earth's magnetic field were collected, it became clear that continents really do move, and that their motion is even more complex and extensive than Wegener originally imagined. One important shift in thinking was this. In Wegener's original picture, continents were like ships moving across a stationary ocean floor. In modern plate tectonics, the plates themselves are the moving ships, made of both continental crust and oceanic crust. The continents are simply the passengers carried along by these plates. 4. Strange but powerful evidence that continents have moved. During the 20th century, scientists discovered many puzzles that could only be explained sensibly if continents and oceans have changed their positions through time. Climate evidence? On Svalbard, Spitsbergen, Norway, an archipelago in the Arctic Ocean, there are large deposits of coal. Coal usually forms from lush vegetation in warm, swampy, tropical or subtropical climates, not in polar regions. Around Greenland, also near the Arctic, geologists found many ancient coral reefs, even though modern corals only live in warm tropical seas. In Antarctica, scientists discovered many fossilized tropical trees, proving that this icy continent once supported forests in a much warmer climate. Conversely, in some equatorial regions of Africa, there is evidence of ancient glaciations showing that these areas were once much colder. All these facts make no sense if continents have always stayed where they are today. They only become reasonable if continents have drifted across different climate zones and latitudes over hundreds of millions of years. Biological fossil evidence. The kangaroo, a famous marsupial, is thought to have originated in the Americas. Yet today, kangaroos are found naturally only in Australia, not in Asia. Such patterns of animal distribution can only be explained if landmasses that are now separated were once connected, allowing animals to migrate, and then later were split apart. Coastline shapes. Geologists and geographers have long noticed that the east coast of South America and the west coast of Africa seem to fit together remarkably well. When continental shelves are taken into account, for example around 1,000 meters depth, the match becomes even more impressive. This led many scientists, including the Russian academic A.N. Kuhn-Mogoy, to conclude that South America and Africa were once a single landmass. Mid-ocean ridges and deep-sea trenches. Around the mid-20th century, scientists discovered that the centers of the oceans are not the deepest areas, as previously thought, but are occupied by huge undersea mountain ranges called mid-ocean ridges. In contrast, the deepest parts of the oceans are the trenches located near continental margins, such as the Mariana Trench, which reaches a depth of about 11.03 kilometers. This trench lies roughly at the same latitude as Ho Chi Minh City and about 315 kilometers east of it. Water mass and ocean area stability. The total mass of water and the overall area of the oceans appear to have stayed relatively stable over very long geological times, even though sea level has risen and fallen during ice ages and periods of marine transgression. This suggests that there are balancing processes involving water being released from inside the Earth and possibly broken down at the surface, leading to a long-term dynamic equilibrium. Taken together, these lines of evidence, climate, fossils, coastlines, seafloor structures, and water balance, all support the idea that continents and oceans have moved and changed shape throughout Earth's history. 5. The widening Atlantic Ocean and the shrinking Pacific Ocean. According to plate tectonics, the rigid outer shell of the Earth is divided into about 6 major plates that are not the same size. The Pacific Plate is composed almost entirely of oceanic crust. Other plates include both continental and oceanic crust. For example, the North American Plate plus part of the North Atlantic form a plate that stretches from Iceland all the way to San Francisco. When two plates move away from each other, the seafloor between them is pulled apart. Along the mid-ocean ridges, the crust fractures, and magma from the mantle rises up to fill the gap, cools, and forms new oceanic crust. In the Atlantic Ocean, the mid-Atlantic ridge runs from the Arctic Ocean down to the Southern Ocean. The ongoing spreading along this ridge causes the Atlantic Ocean to gradually widen. This means that New York and Paris, as well as South America and Africa, are slowly moving farther apart over time. In contrast, when two plates move toward each other, especially where an oceanic plate meets a continental plate, one plate is often forced down beneath the other in a process called subduction. The Pacific plate is moving towards the Eurasian plate. As it approaches the edge of the continent, the denser oceanic crust of the Pacific plate is forced beneath the lighter continental crust, forming a chain of volcanoes and frequent earthquakes along the ring of fire around the Pacific. A similar process occurs along the western edge of the Americas, where the oceanic plate is subducted beneath the continental plates, forming another segment of the ring of fire along the west coasts of North and South America. These subduction zones are responsible for many powerful earthquakes, including the devastating earthquake in Kobe, Japan, on January 7, 1995, which killed about 5,400 people, injured around 22,000, destroyed thousands of homes, and caused economic losses estimated at about $30 billion. In the middle of the Pacific Ocean, seafloor spreading is still creating new crust. However, the rate of spreading there is smaller than the rate of subduction around the edges. As a result, the overall area of the Pacific Ocean is gradually shrinking, while the Atlantic Ocean continues to widen. 6. Continental collision and the formation of giant mountain ranges. When two plates carrying continental crust move toward each other and collide, the situation is different from ocean-continent collisions. Because both are made of relatively light continental material, neither plate sinks easily into the mantle. Instead, the rocks are compressed, folded, and pushed upward, forming huge mountain ranges, often called the roofs of the world. The Himalayas are a prime example. They formed when the Indian subcontinent drifted northward and collided with Eurasia. This collision began tens of millions of years ago and is still ongoing. The Alps in Europe formed when the African plate moved northward and pressed against southern Europe. The Ural Mountains formed at an ancient collision zone within the Eurasian region. Modern measurements show that the Himalayas are still rising by a few millimeters each year, which means that India is still slowly moving northward. This is clear evidence that plate tectonics is not just a thing of the past, but an active and continuous process shaping our planet today. 7. Magnetic field reversals and clues from the ocean floor. Since the early 20th century, scientists have known that in rocks such as clay, lava, and other volcanic materials, tiny particles of iron can record the direction of Earth's magnetic field at the time when the rocks cooled and solidified. When these rocks were heated to a certain temperature in the past, the iron particles aligned themselves with the Earth's magnetic field and then froze in that orientation as the rock cooled. This remnant magnetization allows us to reconstruct the direction of the magnetic field at various times and places in Earth's history. By analyzing these magnetic records from rocks on many continents and islands, scientists found that the North Magnetic Pole has wandered over time. Its past positions do not match its current location. Interestingly, the apparent paths of polar wandering reconstructed from European rocks and North American rocks were different. However, when geologists reassembled the continents according to plate tectonic reconstructions, putting Europe and North America back together in their ancient positions and then letting them drift apart, the paths of the North Magnetic Pole lined up. This is strong evidence that the continents themselves have moved, not just the magnetic pole. Further studies revealed that over the last few million years, the Earth's magnetic field has reversed polarity at least 16 times. That is, the North and South magnetic poles have swapped places. The precise causes of these magnetic reversals are still not fully understood, but they are thought to be related to complex processes in Earth's core. Drilling into the floor of the Pacific Ocean, scientists from Russia and the United States found parallel bands of magnetized rock running roughly north-south. These bands show a striking pattern. Stripes of rock with one magnetic polarity are mirrored on either side of the mid-ocean ridge. Adjacent stripes have opposite polarity. The best explanation is that as the seafloor spreads apart, magma rises along the mid-ocean ridge, cools, and records the magnetic field at that time. Each time the magnetic field reverses, newly formed rocks record the new polarity. Over millions of years, this creates a pattern of symmetrical magnetic stripes on both sides of the ridge. This pattern is one of the key pieces of evidence supporting seafloor spreading and the movement of tectonic plates. 8. Plate tectonics and the formation of mineral and petroleum resources. The theory of plate tectonics not only explains the structure and evolution of the Earth's crust, but also provides a new framework for understanding how mineral deposits, oil, natural gas, and coal are formed and distributed. Knowing that South America, Africa, India, Australia, and Antarctica were once united in the supercontinent Gondwana, geologists can trace ore belts across present-day ocean basins and from one continent to another. Using this approach, scientists have discovered diamond and iron ore deposits in South America and Australia that are extensions of ore belts originating in Africa. Today, the onshore deposits on many continents are relatively well studied, whereas offshore and deep-sea deposits are still only partially explored. However, because continental crust and oceanic crust are structurally linked, understanding mineral deposits on the ocean floor can help us predict deep deposits beneath the continents. Looking at the global distribution of oil and gas fields, we see that most of them are closely associated with large, deep fault systems. Many oil and gas reservoirs occur in rift valleys, regions where the crust has been stretched and broken, especially in the transition zones between continental crust and oceanic crust. These reservoirs are often found in Mesozoic and Cenozoic sediments, which formed at roughly the same time as modern ocean basins. Based on how plates meet, we can distinguish three typical boundary types. Himalayan-type boundaries, where plates collide and compress strongly. Atlantic-type boundaries, where plates move apart and extend, such as at mid-ocean ridges. Mediterranean-type boundaries, where regions experience both compression and extension in a complex way. Each type of plate boundary creates different geological conditions that can favor the formation of particular kinds of mineral deposits. Vietnam, for example, lies at the intersection of two major tectonic and metallogenic belts, the Pacific Belt and the Mediterranean Belt. This gives Vietnam both a rich potential in mineral resources and a complex tectonic setting with significant geological activity. 9. Significance and current limitations of the theory of plate tectonics. Although there are still unanswered questions, plate tectonics is currently regarded as the leading and most unifying theory in modern geology. For the first time in the history of Earth science, a theory about the structure and dynamics of the Earth's crust has been considered significant enough to be nominated for a Nobel Prize, a sign of how important it is. The theory provides us with a golden key to understand the evolution of the Earth's crust, the origin and development of oceans, the formation of mountains, basins, earthquakes, volcanoes, and many other geological phenomena. Using plate tectonics, scientists can better predict the future positions of continents and oceans, assess natural hazards like earthquakes and volcanic eruptions, and design more effective strategies for exploring and exploiting mineral and energy resources. However, we still do not fully understand the deep driving forces that keep the plates moving. The idea of mantle convection, the slow circulation of hot material within the mantle, is widely accepted as a main mechanism, but it may not be the complete story. Like all scientific theories, plate tectonics, no matter how strong its evidence, must remain open to refinement and revision as new data become available. For now, though, plate tectonics remains the most powerful and comprehensive framework we have for explaining the formation and ongoing transformation of continents and oceans on our dynamic planet.